Welcome everyone, and my name is Bert Vermeulen, and I'll introduce myself in just a second. If you have questions as I go through my talk, feel free to put them in the chat box. What we're going to be doing today is I'm going to present to you a lecture that's pretty similar to the lectures that I give in my introductory freshman first semester engineering class. That class is called The Grand Challenges in Engineering, where we look at a variety of things that engineers can do to make the world a better place. And at the same time, we explore various options in terms of students' engineering majors. And so with that, let me start my presentation. And you should now be able to see my slides. And Jackie, if you can monitor the chat window, if anyone has any questions, feel free to pop them into that window. The slide that I'm showing you here now is one that I use at the beginning of the semester and at several other times during the semester. And it shows a launch. And in this particular case, it shows 3 launches of 3 different rockets. They were all launched between about the middle of July and the middle of August. And all 3 of those rockets are going to the same destination, and they took off from 3 different places. The one on the right is a US rocket that was built by United Launch Alliance here in Colorado. The one in the middle is a Chinese rocket, and the one on the far left is a Japanese rocket that has a satellite on it from the United Arab Emirates. The place where all 3 of these rockets are going is to Mars, and they'll get there in a couple of years. So they're off on their journey, and in my class, my students are off on their journey in terms of learning about engineering. And all of these rockets and the things that are involved are a good example of the kind of all the different kinds of engineering that might be of interest to any of you. So with that, let me introduce myself. And I'd like to introduce myself with this picture. I'm the person on the left, and to the right of me is my younger brother. And this picture was taken about a year into college, and I'm in a tent, and that tent was the first thing that I ever designed using the kinds of things that I would need to know as an engineer. So what I needed to do was to calculate all the surfaces of that tent and how to cut the fabric so that when I put the tent together, there would be no wrinkles. So this is an example of the kinds of things that one might try to do, and where one needs the skills of an engineer in order to do that type of work. And to give you a more recent example, one of my hobbies these days is to design bicycles, and more specifically folding bicycles. And what you're seeing here is one of my folding bicycles. These bicycles are designed to fold small enough that they fit into a suitcase like the one that you see on my back there, so that I can fly pretty much anywhere with the bicycle and my gear, and it fits in the same size case that the airlines take as normal luggage. So that's just a little bit about myself. What I want to cover today is a set of topics that are topics that we also have used and slides that I use in my regular class, but they're particular to what might be of most interest to you, as well as giving you a sense of what happens in a typical lecture. So we're going to talk about what is engineering, what do engineers do, and what do engineering students learn. And then I'll give you some sample content of the kinds of work that students are doing on their group project in our class, and the kinds of things that students are learning on one of the topics that we cover, which has to do with energy units and dimensions. So when we get through that, at the end, we'll have some time for questions. But also at a couple of places as I go through things, feel free to ask any questions that you might have by putting them in the chat box. And I'll stop at one or two places and encourage you to do that also, so that you really you get to learn the things that are going to be most interesting for you. So let's start off. What is engineering? And the best way I know to describe it is to talk about the positioning of what is science relative to engineering and what is math relative to engineering. So science, and my assumption is that all of you have taken some science classes in high school at one time or another. Science is there to basically answer the question, how does nature work? And there are various different branches of science. For example, physics, and physics could be broken down even further into mechanics, which is how do physical things move and how do forces on those physical things behave, and electricity and magnetism, which relates to things like how do electronics work, how do magnets work, how do radio waves work, and how do all of these things interact. And also fields like chemistry, biology, geology, astronomy, etc. So science is there to answer the question, how does nature work? Engineering is how you actually make physical things. And at CSU, the types of branches of engineering or majors that one could go into include civil engineering, mechanical engineering, electrical engineering, chemical and biological engineering, environmental engineering, and computer engineering, and also biomedical engineering. So there's a set of different types of courses of study that one could use. And in order to make those physical things, you need to understand how nature works. And the kind of science that's needed varies somewhat from depending upon what kinds of physical things you're trying to make. So for example, civil and mechanical engineers rely a lot on the physics of mechanics. Electrical engineers rely a lot on electricity and magnetism, and chemical and biological engineers and environmental engineers rely a lot on chemistry and biology. There are also other fields of science that contribute in other ways. For example, if a civil engineer is trying to design a dam, they need to understand the geology of the place where they're going to put that dam. The same applies to roads, buildings, foundations, anything of that nature. So there are many different relationships between various branches of science and various engineering disciplines. Now, in order to make physical things, one has to make calculations, and those calculations rely on math. So math is really about how do I calculate different things. And there are different stages, if you will, and levels of understanding of how you make those calculations, which typically start with just normal calculations, basic arithmetic, and then evolve into algebra, typically algebra 1 and 2, geometry and trigonometry. And then once you have mastered those skills, some of you in high school may already start taking calculus. And if you came to CSU to study engineering, you would end up taking 3 semesters of calculus. You would also take differential equations. You'd learn some computer science in terms of how to write computer programs. And you'd be taking statistics, and you might need other math skills as well in order to calculate how to make these various different physical things. Now, I want to make a couple of other distinctions here as well. So computer programming gets used by almost all different engineering disciplines, and computer engineering uses that, but the other forms of engineering use programming as well. So the difference between computer science is in computer science, a typical application might be that you write a program that runs some kind of an app on your phone. Computer engineering uses programming as well, but the programs are inside of whatever device you're making in order to make that device operate. So for example, if you think of a microwave oven has a computer inside of it that responds to you pressing the different touch buttons to make everything operate. A computer engineer would not only design the electronics, but would also design the programs that make all of that work. So electrical engineering and computer engineering are related in that regard, is that in the computer engineers also understand electrical engineering, and they use that to make physical things that also include computers. So that gives you a general overview of how these fields fit together. Now let's talk about what engineers do, and in particular, how do they design and make these physical things? Well, the best way I know to describe that is to start by talking about a typical design process. That design process starts with a particular objective of what it is that you're trying to design. Then the next thing is that you have to acquire data through research in order to understand that particular field and in order to be able to design what you need to produce for that objective. And that research is in two different types of areas. One is from customers, users, stakeholders, where they tell you what they really need the product in order to do. And the other is technical data, which is how do different things work in order to accomplish that objective. One puts all of that together into what's called a specification, which is basically a list of constraints of how the device needs to be able to work and what the technical limitations might end up having to be. Based on that specification, one can generate ideas of how to make something like that work. And then from those ideas, one can select the best ones, and that requires analysis. That's where one does calculations of various different types. And then based on that analysis and that selection of the best idea and the refinement of that idea, one can implement and communicate that design. Now you notice that I'm using two different colors here. So I have green and I have blue. And the reason that I have the green and the blue is that while students are listening to this presentation, I encourage them to take notes. And because sometimes the topics we go through fairly quickly, I tell them the most important words to capture are the ones that are in green. So if you were in this lecture and you were learning this material, my recommendation would be that you would write down all of the words in green. So this gives you the overview of the design process. Now let's dig a little bit deeper. So I've moved that design process to be small on the left, and I want to talk about the analysis piece, this step number 5, because that's where engineers differentiate themselves from a lot of other people, because they have the ability to do the calculation that it takes to verify that something will work and to optimize how it might work. So that analysis process can then be broken down into different steps also. So the first thing is to understand what needs to be calculated. Once you understand what needs to be calculated, you then create a diagram that shows visually how to understand that particular problem. Once you have that diagram, from it, you can then identify what the equations are and what variables you have to solve those equations for. And that's typically called the theory. Once you have the theory, you also identify any simplifying assumptions that you've made. And then with those simplifying assumptions and the theory, which gives you the equations, you start solving those equations and documenting step by step, being very careful not to make any mistakes. And then as you get to the result, you identify that specific result, and in order to make no mistakes, you want to identify what the units would be and what the significant digits would be. And then finally, based on that result, you can discuss and identify any conclusions that you have about that result and how it works. Now, I hope that all of you have been paying good attention to that, because the next thing I want to do is I want to ask you a question and see how well you've learned this material. So the question I want to ask you is the following. And normally in class, we would do this using something called an iClicker. And the question is, step 2 is missing. What is that missing step? So I just need to, give me just a second here. I need to find my menu because I need to ask you that question. And I just remembered I'd forgotten to change my poll here. So just give me just a second. Actually, this is going to be too much work for me to edit this. Ah, yes, here we go. So I'm just going to do it this way. Oh, just a second. There we go. That's not the question we want. We want the second question. Let's see if we can go to that one. Nah, it's going to be too difficult. We'll skip that. But this is the kinds of questions we would typically ask in class. And in this particular case, the right answer would be E. And then we would discuss option E. So option E in this particular case, make a diagram, which is step number 2. What I want to explain next is the difference between a picture and a diagram. So a picture is an actual visual representation of what something looks like. But a diagram is something very different. It is something that is a visual representation to help you analyze something. So it typically includes dimensions, it includes variables, it includes constraints and interactions so that one can see how things work. So let's look at an example of a bridge. So on the left, you see some examples of different bridges. In this particular case, the bridge on the top is what's known as a cable stay bridge, kind of like a suspension bridge, and it's a particular version where the cables actually hold all of the forces. The bridge on the bottom is a computer rendering of a bridge that looks similar to the one on the top, but it actually functions very differently. In the bridge on the bottom, the cables the things that look like cables on the top are actually not functional. All of the structure and the way that things are carried is in the 2 horizontal beams and the diagonals. The way one would draw a diagram for these kinds of bridges or for a cable stay bridge would be the illustrations that you see on the right. And in those illustrations, what you see is a set of lines that show how the different forces in the bridge are actually carried. The bridge on the top is the Erasmus Bridge in the city of Rotterdam. The bridge on the bottom had a design flaw. And that is the bridge that was built, that was intended to be built at Florida International University that actually crashed and fell down and created quite an accident, pretty serious situation, because the analysis that had been done was not complete and had not been done in the way in which it needed to be done to understand all of the forces. So what's important in engineering is the ability to draw those diagrams and then make those calculations. So that gives you an idea of what engineers do and how they do it. So I want to check, does anyone have any questions at this point? Is everyone following along? Are there any things that any of you would like to ask before I continue? And Jackie, anyone have any questions that have come in?
Not at this time. Thank you for asking, though.
Okay, all right. Well, then we'll continue. So the next thing we're going to talk about is we're going to look at two different examples of the types of things that students are doing this semester in this class. So one of them is a group project, and the group project is being done in groups of 3, and it is engineering for catastrophic events. So you see the 4 different pictures there on the left. Students can pick which kinds of catastrophic events they want to learn about and do their research and design some improvement for. One of them is COVID, which is shown by the virus molecule that you see there. Another is impacts on the Earth by asteroids. Another one is coming up with ways to predict volcanoes. And the last one on the lower left is something called coronal mass ejections, which are gigantic electromagnetic storms that would disrupt things like the electrical grid and radio transmissions and things of this nature. So what students have been working on this semester is on a step-by-step fashion, going through and using the design process that we just talked about and the analysis process that we talked about, and using that to actually come up with designs that would engineer our way out of these kinds of catastrophic events. So that's what's happening there. The process that they are using is one where we provide a lot of support. So first off, each stage that I showed you on the previous slide, we introduce it, and then students meet in groups to work on that particular set of deliverables in the form of a report. The report is then reviewed by the graduate teaching fellow for the class, as well as learning assistants who are students who have taken the class previously and have done projects like this as well. So they review and work with the group. The group then polishes based on what they've learned in those reviews. They submit that information, I grade it, and then that is what they use to start working on the next section of the report at the next stage. So they go around this cycle 5 times as they develop their report. Groups work by themselves, and they have different tools available in order to do that. So they need to meet, and they also need to generate the report. So when they're doing their meetings, they can be using Zoom the way that we're using Zoom now, but it's basically in small groups. They can be using other similar tools like Hangouts or Skype. And in some cases, they also meet socially distanced face-to-face in order to work together to develop things. The report is typically done, and some things that don't work as well are trying to text back and forth or use email. The report is typically done on something like Google Docs, or it could be done as a shared document, let's say in Microsoft Word, and the document is shared back and forth in a Dropbox or a shared project folder of one type or another. And that works better, but students have to be very careful not to overwrite what one person has done with things that somebody else is doing. So that's what students have been working on their projects, and they're more than halfway through with those project reports doing that type of analysis. Very interesting work. Now, also in the class, we talk about the grand challenges of engineering for the 20th century or for the 21st century. And we look at the list of challenges that you see there in the tan colored boxes just to the right of the word grand challenges. And students pick which ones of these they are most interested in studying, and then we go into them in more detail. The first projects that students were interested in learning more about were the grand challenges related to energy, which was low-cost solar energy, fusion energy, and carbon sequestration. So we, in September, we worked through a number of topics related to that, and we did that using another cycle in terms of learning and then developing a good, solid understanding. And that cycle starts with in-class activities where we demonstrate things. For example, how the energy in a ping pong ball changes from potential energy when you drop it to kinetic energy as it accelerates. And then when it bounces back up, it changes back to potential energy. We also do various kinds of self-learning, which is through tutorials and the textbook for students to better understand the concepts as part of their homework. Then in the homework, they actually answer questions related to what they have been learning in those tutorials and in class. And then we review what they learned and connect it back with other activities to make things as clear as possible. So, for example, in this field of energy, what we did is we worked through a number of different elements of that. First off, understanding the definition of energy and power, the units and conversions for energy and power, the first law of thermodynamics, energy diagrams, the 5 forms of stored energy, the second law of thermodynamics, what's meant by efficiency, and things that are then more related to solar energy, such as how much solar energy is available, the ways that solar energy can be used, how photovoltaic solar energy works, what materials and what conversion efficiencies are available for doing this, what it costs to have a photovoltaic system and why it costs as much as it does and what can be done to reduce those costs. And then we also talked about nuclear fusion. And then finally, related to carbon sequestration, we talked about greenhouse gases, carbon sequestration, and how that fits with climate change. So we covered all of those. We certainly don't have time to cover all of that here, but I want to give you a little bit of a sampler of the kinds of things that we did. So, and again, we would ask students questions like, can you define thermodynamics? And then students would say, yes, I can define it, and I'm pretty confident. Yes, but I'm not very confident in my definition. Or C, I probably can if I see it in a sentence. Or no, I have totally no idea whatsoever. So let me just ask you, and put your answers in the chat box. So if you were to be asked this question today, would you be able to answer what's the definition of thermodynamics? So tell me which ones of these would best describe your understanding and confidence. So go ahead and put your answers in the chat box. Okay, so I'm seeing lots of people who are kind of in the B and the C category. And that does not surprise me, and you're really no different from the freshman students in my class in that regard either, okay? So what I want to point out is that we will sometimes start out with a difficult question like this, because then when I give the answer, you'll remember it better. So let's go through the answer now. And the definition of thermodynamics, if you were to look it up, We have a reading on it, and in that reading, it's kind of complicated. What the reading says is energy is a fundamental concept of thermodynamics and plays a significant role in engineering analysis. If engineers are to provide solutions to energy-related problems, we must understand energy's fundamental principles. Thermodynamics is one of the major areas of engineering science. So that first sentence is kind of a backward sentence. So you might want to look it up in other places too. So if you were to look it up in Google, it would give you a definition that would look like this: the branch of physical science that deals with the relations between heat and other forms of energy, such as mechanical, electrical, or chemical energy, and by extension of the relationship between all forms of energy. So that might give you a better idea. But what we really want to do is concentrate on something that's a very simple way of remembering this. And that would be thermodynamics is the study of energy. So if you just had that in your notes, you would really have a good understanding of what we would be covering. So with that, let's talk about some of the concepts. So let's define energy, and then related to that, let's define power. The way that energy is defined is the capacity of something physical to perform mechanical work. And mechanical work has a very specific definition and way of visualizing it. It is force times distance times the cosine of the angle between the two of them. So visually, if we were to create a diagram, it would look like this. It would be what's called A dot B. It's something called a dot product, and it's the absolute value of the length of A, the absolute value of the length of B, times the cosine of the angle between them. So if you imagine somebody pulling a brick, and there's an angle of the force in which they're pulling, and the brick is moving horizontally, that angle, the cosine of that angle, is multiplied by the amount of the force and the distance in order to determine the total amount of mechanical work. And if you wanted to learn more about that, you could then research more about that, and that would be the kind of thing that students might do using Google, YouTube, and a good search term would be something like dot product physics. So that is energy. Power is the rate of energy. So it is energy per unit of time. Now let's understand that a little bit further, because in order to be able to do calculations, you have to understand the details. So that gets into units and conversions. So we have the definition of energy, the capacity for doing mechanical work. Work, force, is times distance times the cosine of the angle is work. That's what we had from the last slide. So then, if we had the two lined up, we can get rid of the cosines. Now we're going to talk about force and distance and the appropriate units in order to develop the units for energy. The International System of Units has the meter as its unit for distance, and that is a base unit. It's something that is specifically measurable by itself, and you can't make it any simpler than that. So that's distance. Force is measured in something called a Newton, and a Newton is a derived unit, which means that it's a combination of other more basic units. A force, so the unit for energy is going to be newtons, which is force, times distance, which is meters. So Newton meters, and that's called a joule. And you see the third way I've described that is kilograms meter squared per second squared. And now I'm going to show you how you get there. So force can be broken down into mass times acceleration. And mass has a base unit of kilograms in the international system. And acceleration is distance divided by time squared. And the base unit for time is a second, and for distance, we already had it, is a meter. So therefore, force would be kilograms, which is the mass, times acceleration, which is a distance over time squared, which is meters per second squared. So that gives us force. Force times distance is energy. So we have another distance in there. So it turns to kilogram meters squared per second squared, which is what I have in the green box. And that gives you the units for energy, which is also called a joule, and that's a derived unit. Power is energy per unit of time. And so the units for power are going to be joules per second, which is defined as a watt. 1,000 watts equals 1 kilowatt. And a way that we normally think of power is in the form of horsepower. And there's relationships between kilowatts and horsepower, because horsepower is basically in the older English system. And then in the English system, there's also ways of measuring energy as a distance, which is feet, and a force, which is pounds. You can also measure it as being watts down below multiplied by seconds. And you could have 1,000 watts equals a kilowatt, and 3,600 seconds equals an hour, which would give you a kilowatt hour. So that's energy units. Now let's talk about the diagrams that get used for energy. It's things like this. So potential energy is mass times the acceleration, which is due to gravity, times height, mgh. And then you can see the definitions there. M is mass, g is gravity, which on Earth is about 10 meters per second square, and h is height. So the higher you lift something, the more energy it has. And just to give you an idea of what a joule is, if you were to take your cell phone, which has a force of about 2 newtons, and you were to lift that by 50 centimeters, which is about 1.5 feet, that would be equal to about 1 joule of mechanical energy in the form of potential energy. So the first law of thermodynamics says that energy can never be destroyed. There's always the same amount of energy available. It just changes. And so that's also called conservation of energy. And here's a diagram that shows all of the energy in the US in 2019 and where it came from, how it got converted, and what happened to it at the end. So you can see solar, nuclear, hydro, all the way to petroleum. And the total, if you were to total it here, and the total, if you were to total it here, are the same. And here's how it flows through our economy, what we use it for, how we use it in order to get to these end results. So these are the kinds of diagrams that we then study as we go through the different classes. And I'm not going to spend a lot of time on it here, but just want you to be aware that here's how it works. The typical diagrams that we use in thermodynamics problems are all based on some system or process having different inputs and different outputs. And because of the first law of thermodynamics, the sum of the inputs, so the total amount that goes in has to equal the total amount that goes out. And that's what I showed you on this diagram as well, that in every column where you look at this, the totals stay the same. All we are doing is converting it from one place to the other. I talked about one form of stored energy, and I want to talk about the other forms that energy can be stored in. So remember that energy is the capability for doing mechanical work. And these are the 5 ways that we can actually store energy. Potential energy, kinetic energy, internal energy, chemical energy, and nuclear energy. And when you convert from one to the other, the total has to stay the same. Gravitational potential energy is what we showed you in the diagram. Mass times the acceleration due to gravity times height. You can also have potential energy in springs and in an electromagnetic potential energy, which would be stored as a voltage times a charge. And if it's in a spring, it's called elastic energy. And it's also the force of moving the spring times the distance that you've moved it. Kinetic energy is the energy of motion. Things move based on a velocity, and it's calculated based on 1/2 of the mass times the velocity squared. Internal energy or thermal energy is heat, and it's calculated based on the mass of something, a coefficient for how much the temperature changes as the energy increases, and the amount that the energy changes, which is shown here as delta T. Chemical energy is things like the energy that is derived from burning something, where you actually change from one kind of molecule or one set of molecules to a different set of molecules. Typically, you have to put in some energy, and then energy is released, as shown by the graph here. And nuclear energy is based on changing the mass of something, and it's how hydrogen fusion works, and it's also how nuclear bombs work, and it's based on the equation E equals mc squared. So that's a lot of material that I've covered so far. Do any of you have any questions about any of that? This is a good time to ask questions. And if you don't have any immediately, I'm going to show one more slide, and then we're going to wrap up. And the slide I want to show you is what kinds of technology students actually use in the class in order to learn this material. And that in the class this semester, we are primarily face-to-face, but we also use tools like Zoom. So every student should have a computer, Windows or Mac, a microphone, a webcam, and a mouse, just like what you have here in order to be able to be on Zoom. And computers are also used for some other things, which I'll explain in a second. Every student needs a smartphone because that's how we do some of the interactions with some of the systems that we have as well. And every student should have some way to take notes, which can either be paper and pencil or pen, or using a tablet or stylus. And then the computer obviously needs to have an internet connection so that you can connect to various different tools that you will use. You also connect to our learning management system through your phone and through your computer, which is how assignments are presented to you and grades are presented, and all the various different resources that you would be using for your homework and for your group project are presented to you. In addition, we use an application which allows students to vote. It's something called iClicker Cloud, and it's free. All students get free access to Microsoft Office. All engineering students get access to something called Virtual Classroom, which gives them access to all kinds of other useful software. So for example, computer-aided design software, such as AutoCAD. You also use your computer for times when we might have video meetings of various different kinds. And then finally, we also have an online textbook that we use for learning some of the content and making sure that you learn it well. So that is really a very quick summary encapsulating some of the types of things that we would typically cover in class. And at this point, I'm finished with everything that I wanted to present. And this is a good opportunity for you to ask any questions you might have on any of the things that I've talked about, or anything related to engineering and the study of engineering. So feel free to pop in any questions you have. So what's interesting is I gave this same talk about a month ago, and then I had an audience of one student like you. And when I had an audience of one student, I had lots of questions. So, okay, good. We got our first one. Thanks so much, Ephraim. Are engineering courses more project-based learning over lectures? So, in general, you will, in your first year, you will have one or more project-based learning classes. And then in each of your following years, you will typically also have some project-based learning classes until you get to your senior year, when almost all of it is project-based. You will have lectures, so you will have class times, but the things that happen in class times are changing from the kind of lecture that you saw here today to ones where you're doing more and more activities during the class time, or the entire class is actually activity oriented. So some things are project oriented, but there's also a lot which I would call activity oriented, where you do things and get to see how they work. Okay, so Ryan asked the question, I'm looking to transfer for this upcoming spring. Will classes be online or half and half like this semester? So I don't think that there's been any official word, but what I would expect is that classes will more likely be more face-to-face than they were this semester. So as we learn more and more about how to control the coronavirus, we will be able to open up more and more things and make them more interactive and more face-to-face. So I know that that's something the university is working very hard on. They're making good progress on various different ways of keeping the environment safe. And so I would expect that in the spring, if you want to be more face-to-face, you will have that option. And if you want to be online, that option will continue to exist as well. Good, those are good questions. For the reports and engineering courses, will LaTeX be used? You can use LaTeX, you're not required to. You can just simply use word processing software like Microsoft Word or Google Docs. It is to your benefit to learn how to use those word processing software really effectively, because it will make your reports look better and it will make you more productive. So really good question. So other questions about how we teach, the kinds of things you would learn, and the kinds of things that engineers might learn versus other going into other majors.
Well, I was wondering if you have any advice for students on how to pick a major, maybe if students are considering multiple majors at this time. Any tips or tricks that you would provide for students on choosing a major within the College of Engineering?
So the most important question to ask yourself, not just whether you're going to study engineering or something else, is what do you enjoy doing? Because if you pick a major based on something that you enjoy doing, and that becomes your career won't feel like work. And you'll just be overjoyed that they're paying you to do something that you enjoy anyway. So that would be my number one tip for any of you. So really try to understand what you would find interesting. And related to that, what would you think would be really cool if you would be able to do it? So remember, I showed you my tent at the beginning. I thought it would be really cool to be able to design a tent like that. So that's the kind of thing. Okay, Marcel has a question. I'm looking to study nuclear engineering. I know there is no true concentration or major at the school. Is there any discipline of engineering that would learn more in that direction for later on? So I think CSU actually does students a favor by not having too many choices of different engineering majors. Because if you wanted to do something like nuclear engineering, you could approach it from a lot of different angles and you'd still end up in that same field. So the two majors, actually three majors that would make sense in this particular case, well, in fact, all of them do. Let me explain how all the different majors might relate to nuclear engineering. So the construction of nuclear reactors would be civil engineering. The actual way the physics works in nuclear engineering is most closely related to chemical engineering, because what you are doing is you are making the chemical fuel source from nuclear materials. So chemical engineers would typically know a lot about that. And people who are making nuclear fuel would most likely have something related to chemical engineering in their backgrounds. The actual way that the entire nuclear reactor works with all of its pumps and cooling systems and all of that, those pumps and cooling systems, chemical engineers will understand, but the specific pumps and things would typically get designed by mechanical engineers. When you think about getting the power out of that and some of the physics involved, you're going to see that electrical engineers get heavily involved in that. And it's also good to understand a lot of the physics. Does CSU offer many clubs or opportunities to further explore what interests me? Yes, I believe that there's approximately 20 different clubs that are engineering related clubs. So some of them will be like IEEE, which is the Institute for Electrical and Electronics Engineers, so it's very specific. Some of them are clubs like Engineers Without Borders, which has engineering students from all kinds of disciplines in there. Others will be things like the Rocket Club, where they actually build rocket engines. So Jackie's also given you a link to all of the clubs and how you can look them up. And was I about right that there's about 20 of them?
Yes, and there's more clubs as well. So there's societies and clubs. So our societies, we've got our American Society of Civil Engineers and Mechanical Engineers, and then we've also got our diversity programs in engineering. And then I'm going to drop a link for all of the other CSU clubs and organizations, of which there are over 500. So there's tons of ways to get involved outside of engineering as well. So I'll drop that in the chat. And then it looks like there's a question about internships as well, with business associated with specific degrees. So definitely, if you want to talk, Bert, a little bit about those internship opportunities, that would be awesome.
Yes, yes. And there's different ways to be doing internships. Some of it is summer internships during summer breaks. And through the career programs, you can contact different employers, or employers will contact you in order to be able to do that. There are also opportunities for students to be doing internship on research projects on campus. And I want to give you one example of a student who has done particularly well on this. She is going into chemical and biological engineering. And so she's very interested in the engineering of how you treat cancer. And so there's a number of labs at CSU, both in the College of Engineering, but also in a number of other places in biochemistry and physiology and things of this nature. And so she was able to volunteer to work in one of those labs. She did that for a semester. And then after she did that, she found outside internship programs. And she's actually going to be taking all of next semester and working at the Fred Hutchinson Institute in the Seattle area, specifically on engineering cancer cells and how to prevent cancer in laboratory rats. So yes, the point is that those opportunities exist. What you need to do is exactly what Trent does, is ask questions, talk to your professors, and then based on that, or I guess it wasn't, it was Ephron who was asking that question, based on that, you will then be able to find places and to be able to take that further. And Jackie's just given you a link as well to the Engineering Success Center and some of the different programs that are available there. These are really good questions. Okay, so Hero Trent, I know CSU doesn't offer an environmental science degrees, but how does environmental engineering relate to environmental science? I think CSU does have environmental science. But the question is really a very good one. And let me give you the difference between environmental science and environmental engineering, and then I'll give you the difference between science in general and engineering in general. So in environmental science, just like what I showed you in that slide where I talked about science is about understanding how nature works, environmental scientists will typically be taking lots of measurements of things and then understanding what those measurements mean, because they're trying to understand nature. Environmental engineering is about cleaning things up. So once you have measured things and you find out that this mine that was there 100 years ago created all kinds of hazardous waste, an environmental engineer would design and build a system for cleaning that up. So you study the same science in environmental science as in environmental engineering, but environmental engineers do a lot more studying of math and the design process in order to actually be able to come up with solutions. And the same applies to a lot of other fields too. So biology versus biological engineering, chemistry versus chemical engineering. Biological and chemical engineers will design systems. So a biologist might understand how yeast makes, or how bacteria make yogurt. A chemical engineer would design a factory to make the yogurt that is based on that science. So that's how the two would relate. Really good question. And you can see that Jackie's provided several links that give you more information about ecosystem science and sustainability, which is basically environmental science, and then also interdisciplinary environmental studies. Good. Any other questions before we wrap up? Because I think we're about at our scheduled closing time. So any last minute questions before we finish?
Yeah, I figured I'd just speak about it before I run out of time typing. Specific to the nuclear engineering, would then environmental engineering be more consistent with waste management of radioactive waste?
Yeah, yes. And there are actually professors at CSU that work on those fields.
Okay.
So,
that's more
so if you wanted to work on that aspect of it, yeah, CSU would have it.
Okay. All right. Thank you.
Yeah. Okay, and you all have Jackie's email address if you have follow-on questions, and then Jackie can forward any of those to me as well. So thanks all of you for joining. I hope you found this informative, and I do hope to see you at CSU sometime in the future. Bye, y'all.
Thank you. Thanks so much. Enjoy the rest of the day. Awesome. Great. Well, I'm going to go ahead and shoot off as well. Thank you so much for that presentation.
I think that worked very slick. So I'm glad we had
Definitely.
the audience size that we did and good questions and all that. I hope it met the needs of all those prospective students as well.
Awesome. Thank you so much. I appreciate you.
Okay, bye.
Have a good one. Bye.